Welcome, Class 11. Let's kick off today's explainer by talking about a massive challenge in physics, one that literally affects scientists all over the world every single day. We're talking about the very language of reality, measurement. Because honestly, without a common language, the universe is just a confusing jumble of numbers. So, how exactly do scientists worldwide agree on measurements without totally confusing each other? This question hooks right into the absolute chaos of localized measurement systems that used to be the norm. I mean, imagine ISRO trying to build the Chandrayaan rover with parts from 3 different countries, and none of their rulers match up. Absolute disaster, right? Well, for a very long time, that was a huge, genuine hurdle in science. Okay, let's dive right into our roadmap for today. We've got 1. Past measurement chaos. 2. Enter the SI system. 3. The 7 base units. 4. Plane and solid angles. And 5. Derived units and guidelines. Section 1. Past measurement chaos. Historically, scientists in different countries were using entirely disconnected systems to measure the exact same things. You had the CGS system relying on the centimeter and gram, the British FPS system using the foot and pound, and the MKS system working with the meter and kilogram. Literally only the second, measuring time, was a universal point of agreement. You can imagine the massive headaches this caused when trying to share research across borders. Section 2. Enter the SI system. So, we transition from that localized chaos to the ultimate universal fix. Developed in 1971 by the International Bureau of Weights and Measures, this system standardized scientific, technical, and commercial work globally. It gets its abbreviation, SI, from its French name, Système International d'Unité. This became the baseline, ensuring that a meter measured in Tokyo is exactly the same as a meter measured in Mumbai. Now take a look at the year 2018 here. This is super interesting because the SI system was actually revised recently. Science is always evolving, right? As our technology gets better, our ability to define measurements with mind-bending precision improves, which means we occasionally have to update the very definitions of our base units. But why use it? Well, the absolutely crucial point is that the SI system uses decimals. Think about the old British system, 12 inches to a foot, 3 feet to a yard. It's mathematically exhausting. The SI system, being decimal-based, makes all those terrifying unit conversions a total breeze for your physics problems. You literally just shift the decimal point. It's elegant, simple, and internationally understood. Section 3. The 7 base units. All right, let's look at the absolute foundation of the SI system, its 7 core building blocks. These are the anchors for all of physics. We've got length measured by the meter, mass by the kilogram, and time by the second. For electric current, we use the ampere, thermodynamic temperature is in Kelvin, the amount of a substance is the mole, and finally, luminous intensity, basically how bright a light is measured by the candela. To give you a taste of the incredible precision we're talking about, look at how the mole is defined. It's not just some arbitrary chunk of stuff. It contains exactly 6.022140076 times 10 to the 23rd power of elementary entities. This fixed number is the famous Avogadro constant. And remember, when we use the mole, we always have to specify the entities, like whether we're counting atoms, molecules, or electrons. Now, before you start panicking about memorizing 10-digit numbers for your exams, let me reassure you with this direct textbook quote. You absolutely do not need to memorize these complex definitions. Seriously. They are just provided to show you the staggering extent of accuracy in modern physics. The big takeaway here is an appreciation for that precision, definitely not rote memorization. Section 4. Plane and solid angles. Besides those 7 base units, there are 2 supplementary units specifically for measuring angles. Let's compare them. A 2D plane angle, which measures the slice of a flat circle, is the ratio of the arc length to the radius, and its unit is the radian. On the other hand, the solid angle deals with a 3D cone cutting into a sphere. It's the ratio of the intercepted spherical area to the square of the radius, and its unit is the steradian. Now, this is a vital physics fact to remember. Despite having unit names and symbols like rad and SR, these two angle measurements have absolutely no underlying dimensions because they are just ratios of a length to a length or an area to an area squared. The physical dimensions actually cancel out. They're basically pure numbers that give us geometric perspective. Section 5. Derived units and guidelines. Finally, let's see how we build out the rest of the massive physics universe from just those foundational pieces. Watch how the SI system logically expands to cover everything. Want to measure speed? You simply divide length by time to get meters per second. Need to talk about huge or incredibly tiny numbers? We just slap on prefixes like kilo for 1,000 or milli for 1,000th. The whole system snaps together perfectly, kind of like molecular building blocks. Keep in mind, there are strict reference guidelines for all these symbols to maintain that crystal clear international communication. Interestingly, some derived units get special names to honor scientists, like a kilogram meter per second squared simply being called a Newton. And a few non-SI everyday units are still kept around just for sheer convenience. Things like minutes and hours, because, let's face it, trying to schedule a lunch in thousands of seconds is just way too much work. So the pursuit of perfect measurement is never really over. Since the definitions of our base units are continually revised to keep up with progress, just like we saw with those 2018 revisions, I'll leave you with a question. As technology continues to improve, which definitions will scientists be forced to revise next? As we build better lasers and atomic clocks, who knows what a second or a meter will even look like a century from now? Thanks for joining me on this explainer, and keep questioning the reality around you.